How's it going, ladies and gentlemen? Mr. Donnie here again. This time we're going to take a look at some practice problems regarding the strength of covalent bonds. So number one, circle the correct options of the bonds: carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. The carbon single bond is the longest and the weakest. Right, so single bonds, longest, double bonds, shorter than that, triple bonds, even shorter than that. The single bonds the easiest to break, the weakest, and triple bonds would be the strongest or the hardest to break. Using the table of average bond energies below, calculate the delta H for the reaction. So they give you the structures and they give you the bond enthalpies for breaking those, and you got to figure out, well, what's the change in energy? Remember, whenever you're breaking bonds, you're adding energy. And whenever you're making new bonds, it's releasing energy. So if we want to know what is the overall change, you got to look at how much energy did you put in to break all those bonds, how much energy did you get out making new bonds. So on the reactant side, we have carbon-hydrogen bonds, we have carbon-carbon triple bonds, and we have hydrogen iodide bonds. So if I take a look, how many carbon-hydrogen bonds do I have? Looks like I got 2, and they're each worth 413. So in order to break those 2 carbon-hydrogen bonds, I need to invest 826 kilojoules. Now the carbon-carbon triple bond, there's only one of them, so I can just look it up. There's 839. So to break that triple bond, I have to put in 839 kilojoules of energy. For the hydrogen iodine bond, there's 2 of them because of this 2 right here. So it's saying that we have 2 molecules of HI. So I have to break 2 HI bonds. So 2 times 299 gives me 598. So when I add all those together, I'll get how much energy I had to put in to break all those bonds. When I do that math, I end up with 2,263 kilojoules to break all those bonds. So now I can take a look at my products. And what bonds did I make? Well, I still have carbon-hydrogen bonds. I also have carbon-carbon single bonds, and I also have carbon-iodine single bonds as well. So let's start with carbon-hydrogen. I have 4 of them. They're each 413. So when I make those 4 bonds, I end up with 1652 kilojoules being released. That carbon-carbon single bond, I only have 1 of them, and it is 348 kilojoules. So when I make that bond, it's releasing 348 kilojoules. And the carbon iodine bonds, well, I have 2 of them, and they're each 240. So when I make those new bonds, I end up with 480 kilojoules being released. So when I add all those together, I end up with 2480 kilojoules being released. So the overall delta H, well, I had to put in 2,263 kilojoules to break all those bonds, and then I released 2480 kilojoules. So that's a negative value. And then I do that math, and I end up with a negative 217 kilojoules as my final answer. Or number 3, using the table of average bond energies below, calculate the delta H for reaction. So same process. So let's divide that down the middle, take a look at what I have to do with the reactants and the product. So I got hydrogen carbon bonds, I got carbon carbon triple bonds, and I got hydrogen iodine single bonds. So how many hydrogen carbon bonds do I have? There's 2 of them. They're each worth 413. So to break those 2 bonds, I have to invest 826 kilojoules. The carbon-carbon triple bond, there's only 1 of them. And again, it's 839 kilojoules. And the hydrogen iodide bonds, this time there's only 1, so 299. So in order to break all those bonds in the reactants, I have to invest 1,964 kilojoules. Now the products, I might have to draw this out. So CH2, carbon, and then HI, The reason I have to draw this out is because now I can see that there must be a multiple bond in that molecule that they didn't show. So now I go, all right, well, carbon-hydrogen bonds. I have 3 of them, and they're each 413. So when those 3 bonds are made, they release 1,239 kilojoules. There's also a carbon-carbon double bond. When that bond is made, it releases 614 kilojoules. And then there's also a carbon iodide bond, which when it's made, releases 240 kilojoules. So when I add all those together, I get a total of 2,093 kilojoules being released. So if I want the change, well, let's see, I had to invest 1,964 kilojoules to break the bonds, and then I released 2,093 kilojoules making the new bonds, which means my overall change is negative 129 kilojoules. All right, number 4, from the information given below, calculate the heat of combustion of methane in kilojoules per mole. Start by writing the balanced equation. So we're combusting methane, so we start with CH4, and combustion always reacts with oxygen and makes carbon dioxide and H2O, water. So now I have to balance it. So well, I'm just going to cheat, right? You don't know how to balance, watch the video about balancing. There we go, everything's balanced now. And now I might want to draw out the structure so that I can see what kind of bonds I have going on. So CH4, there's 4 carbon-hydrogen bonds. In O2, there's a double bond, and there's 2 oxygen molecules, so there we go. I make a CO2, so C double bond O, and 2 H2Os, so H bonded to O, and then boom. So now I can see all the bonds that I got going on. So in order to break the bonds, I need to invest some energy. So let me take a look. I got carbon, hydrogen bonds, and how many do I have? Looks like I got 4 of them. So 4 times 413 tells me to break all those carbon hydrogen bonds. I need to invest 1,652 kilojoules. I also have oxygen double bond, and there's 2 of them because there's 2 of those molecules, each at 495 kilojoules per mole, which gives me a total of 990 kilojoules I need to invest to break those bonds. So in total, I need to invest 2642 kilojoules to break all the bonds. And now new bonds that are being made. Well, let's see, I got carbon, oxygen double bond, and there's 2 of them, and each of them is 799. I'm kind of running out of room here, which means, what's that come out to be? 1598 kilojoules of energy going to be released when I make that CO2 molecule. Now the HO bonds, well, there's 4 of them total because there's 2 in each water molecule, and each of them is 463 kilojoules. So when I do that math, I get 1852 kilojoules being released when those bonds are made. And when I add those together, I get a total of 3,450 kilojoules of energy being released. So if I want the overall delta H, I have to invest 2642 kilojoules, and I release 3450 kilojoules, which tells me that the difference is a negative 808 kilojoules per mole as my final answer for this problem. All right, number 5, calculate the delta H for the reaction below using the table of average bond energies given. So we got C triple bond O, I got 2 H2 molecules, so it's really HH, and there's another molecule of that, so there we go. Okay, H3C, so that's carbon with 3 hydrogens bonded to it, and then bonded to that carbon is also an oxygen, which is bonded to a hydrogen. So let's do some math. All right, in order to break this carbon triple bond to oxygen, well, there's only 1 of them, and it's going to take 1,072 kilojoules to break that. I also have to break these hydrogen-hydrogen bonds, and because I have 2 molecules of H2, there's 2 of those bonds I need to break, and they're each 436 kilojoules, so that gives me a total of 872 kilojoules I need to invest to break all those bonds in the reactants. Now in the products, I have a hydrogen carbon bond, and there's 3 of them. So let me look up, each of them's 413. So 3 times 413 equals 1,239 kilojoules of energy being released when those bonds are made. I have a carbon-oxygen bond, and I only got one of them, and that is 358 kilojoules. So I release 358 kilojoules of energy when that bond's being made. And then I also have an oxygen-hydrogen bond, and there's only one of them. That's going to release 463 kilojoules of energy. So when I look at the bonds being made and I add all those together, I'm releasing 2,060 kilojoules of energy. When I do it for the reactants and I add those together, I have to invest 1,944 kilojoules of energy. So the overall delta H is going to be, well, I invested 1,944 kilojoules and I released 2,060 kilojoules, making the new bonds. So my overall change is going to be negative 116 kilojoules per mole as my final answer. All right, I hope you found that helpful. I'll see you in class. Okay, bye.